when the eigenvalues or the eigenvectors are to be determined for a real symmetric matrix, then one can use a better algorithm, what we call as a Jacobi rotation. Okay, what is the requirement is the matrix should be real and symmetric, as well as the eigenvectors should be non-degenerate. So that is a general case. We are not going to deal with any degenerate eigenvectors. So under that, when your given matrix A is real and symmetric, then this Jacobi rotation algorithm, it provides you a very efficient way to deduce all the, I wouldn't call efficient, in an easy way, to deduce all its eigenvalues and the eigenvectors. Okay. So before we go into this Jacobi rotation, a small recap is required. So if you remember, what we discussed in the earlier class is, so we had what the problem we are going to deal is, your matrix A dot x, a vector, will be lambda x vector. So when under this condition, when you are multiplying the x from the right hand side, then you call this vector as right eigenvector. Okay, this is the eigenvalue problem we are solving. So we will call this a right eigenvector. On the other hand, you can have another left eigenvector also, which we discussed in the earlier class. You can multiply the matrix, the vector from left hand side, then it makes xl vector dot a vector, this will be xl vector, that will be equal to lambda times xl vector. So this is called as your left eigenvector. So this is right eigenvector and this is left eigenvector. So let us see. For example, we also saw that when you take a transpose of it. So when you take transpose on both the sides, what you are going to get is A transpose dot xl transpose will be equal to lambda times xl transpose. So what it says is the left eigenvector is nothing but the transpose of the right eigenvector of the A transpose. And if your A is symmetric, then we have A equal to A transpose, and that condition, this equation is going to become, so A matrix, so this is matrix, A matrix will be XL transpose, that equal to lambda XL transpose. So under this condition, so a left eigenvector is, and the right eigenvector, this is right eigenvector, right? So the right eigenvector, the transpose of the right eigenvector is a left eigenvector, or that's what you call FL will be XR transpose, or either or the other way, what you written here is the other way. So XR, this is XR vector will be equal to transpose of the left eigenvector. And then we also saw something when we construct all these eigenvectors. So when we construct all the eigenvectors, when we obtain all the eigenvectors of the matrix, right eigenvectors as a left eigenvectors, then we can combinedly collect all their eigenvectors together and form a square matrix, and we denoted it as XR. This is a square matrix which is a collection of right eigenvectors, that is right eigenvectors will be a column vector, and then we can another matrix we constructed SL matrix will be a collection of all left eigenvectors, which is basically row vectors. So by this we can construct the n cross n matrix for an n cross n matrix of eigenvectors from an n cross n A matrix. Okay, so for this you don't need to have the symmetric or something. And then we also saw one more property. What happens? So A matrix dot XR matrix, the eigenvalue problem, what we wrote can be written as this will be your XR matrix dot diagonal. So that will be your eigenvalues 1. This also we saw. Okay, this is simple to prove from here. So the same equation, if you write it like this will be in this form. Fine. And we also saw XL matrix dot XR matrix is the product of this is a diagonal. matrix and diagonal matrix. Okay, say something, it's a diagonal matrix. So, and if you are able to properly normalize, this diagonal can become an identity matrix. If you do some proper normalization, you can actually write this product to be an identity matrix. So once it's identity matrix, so what it says is your XR inverse will be equal to XL. So this is for any general matrix, no need to be a real symmetric matrix. And now if you compare, so for a symmetric matrix, what you are the right eigenvector is equal to transpose of the left eigenvector. So then if I convert this in terms of matrices, what will you have is, so for a symmetric matrix, XR matrix will be a transpose of XL matrix. Okay. So, and then what we can do from this equation, so if we write from this equation, if I multiply from X inverse from the left hand side, so what we are going to get is XR inverse dot A matrix dot XR matrix will be equal to a diagonal, because this will become identity matrix. So diagonal of lambda 1 to lambda n. This is nothing but a similarity transformation. So the matrix XR, which can diagonalize your matrix A, then what happens? That matrix, the column of those matrix will be the right eigenvectors, and the diagonal elements will be the corresponding eigenvalues. So now for a case of symmetric matrix, we found XR inverse will be equal to XL vector. So therefore, XL matrix. So this can be written as XL matrix dot, this is a case for a symmetric matrix A. So XR, that will be equal to your diagonal element of lambda 1 to lambda n. And now XL, okay, yeah, from here I can write XL is nothing but a transpose of XR. So this will become XR transpose dot A matrix dot XR matrix equal to diagonal of lambda 1 to lambda n. So now this is interesting. So for a symmetric matrix, what we have to identify is, we have to identify the similarity transformation that, say for example, maybe a matrix is something like your Z matrix. I am calling it a Z. Z transpose dot A dot Z. So the matrix which diagonalizes A So then, once after diagonalizing, the diagonal elements are your eigenvalues, and the columns of the matrix which is diagonalized is going to be the eigenvector. So this is the property which is used in a Jacobi rotation to identify the eigenvalues and the eigenvectors. How are we going to do about it? Well, fine. So before we look into it, so I want to say, okay, so in a Jacobi iteration, we will do it. Iteratively we try to diagonalize the matrix, that we will see it later anyway. So now before that, I want to show you where this one. Yeah, fine. So this equation, if you see this equation, the matrix. So okay, XL is XR transpose, right? So XL will be XR transpose. So this we can write it as XR transpose dot XR is an identity matrix. So if you see, there is one simple matrix which we see often, which satisfies this property. That is what your rotation matrix. For example, if I call rotation matrix, what we all know rotation matrix is cos theta sine theta, minus sine theta and cos theta. So this matrix have the property R transpose dot R equal to I. So somehow we can employ this rotation matrix because this has satisfied the property what we want to have, this transpose property of this. So if we can exploit this matrix somehow for our n, this is 2 cross 2 matrix, for our n cross n matrix, and try to make this transpose this matrix Z. So I will try to get this matrix Z somehow from this rotation matrix, and if I am able to diagonalize the matrix, then my problem is solved. So that technique, how we are going to use this rotation matrix to diagonalize this matrix A, that technique is called as your Jacobi rotation. So instead of writing it cos theta sin theta in a simple form, we will write it as C S minus S and C, where C represents cos theta, S represents sin theta, and we will go on. Even when we write T, it becomes tan theta. So we will not write in a tan or long way. We write in a shorter form like this. Fine. So how are we going to do it? So now in a Jacobi rotation, so what we do is we are going to iteratively going to convert this matrix into a diagonal matrix. How are we going to do? Let me take for example one operation. So let me call it as the matrix P1 dot A matrix, transpose and P1. This will make an A prime matrix, and the A prime matrix is something, this operation will make one diagonal element. So maybe for the A matrix what we are having, so if we have a A matrix, so one of diagonal, so this is the diagonal element. So this operation, after performing this operation, when you make it A prime, one of the diagonal element will made it to 0. Diagonal element and off diagonal element, because it's symmetric matrix. So and then I repeatedly then I do it another operation, that is P2 transpose vector. I do it on my modified matrix A prime dot P1 matrix. So already we have made one diagonal element 0. This operation will make some other diagonal element 0. I keep on doing to make all my diagonal elements 1/2. The one you do only here, automatically this will become 0 because it's symmetric matrix. So one by one I will keep making all the diagonal elements 0. So I will keep repeating this multiplication of this matrix again and again. So then what happens? So when I combine, so if you see, if I substitute A prime, so what you will see is, so from here, if the same thing I can write it as P2 transpose dot in the A prime, instead of A prime I can write this. So this will be P1 transpose dot A, that's our original vector, original matrix given, for which we are finding the eigenvalues and eigenvectors, into P1 dot P2. So this is what. And if I keep repeating it such that finally my A becomes diagonal, so that means I will keep multiplying with all the Pn times, Pn iterations, so means m iterations, or whatever iterations I need to require to make it all the elements to be, all the off diagonal elements to be 0. So when you construct this all matrix, then the product of all this matrix, what I made, let me call it as V. V will be P1 dot P2, P3, go on. So when the product of all this matrix, which I will call it as V, and that will be our right eigenvalue, or the transpose of it will be the left eigenvector. Okay, so the column, each column of the matrix V is our eigenvector, and the diagonalized matrix, for which the diagonal elements, each diagonal element is the corresponding eigenvalue. So in this process we can identify, so we can find out all the eigenvalues and the eigenvectors of a real symmetric matrix. Okay, now the point is how we are going to construct this matrix P. So as I said, we have to construct this matrix P to construct, we get an idea from this rotation matrix, because this rotation matrix have a property R transpose R equal to Y, which satisfy our requirement. We will try to get this P from this rotation matrix. So what am I going to write? Let us write the P matrix to be an identity matrix. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So what am I going to do is, so I will make an identity matrix, and somewhere else I pick up some square element, maybe here or anywhere else along the diagonal. So for example, let me take out this square element. What is that where we are having? Yeah. So let me write down matrix. Say for example, I will replace one of these two diagonal elements with C. For example, I am going to replace these two diagonal elements with C. And the corresponding off diagonal element, I will make it as S, and this as minus S. So, and what I did, I took an identity matrix, took two diagonal elements as C, and along the same row, means I make a complete square by maintaining the off diagonal element as minus S and S. So this is how I can keep constructing we will construct our matrix, the matrix which is going to eliminate one of the diagonal element of diagonal element of A to be 0, like this. So this I can call it as, so this is what? Second row and 1, 2, 3, 4. Second row and 4. So I'll call it as 2, 4. So what it says that means this is the second row and this is the fourth row, and similarly this is the second column and this is the fourth column. So what it says is, when I write P24, the P24 is an identity matrix except the diagonal element corresponding to first PP, that is 2, 2, that will be C, and corresponding to 4, 4, that will be C, and the off diagonal element corresponding to 2, 4 will be S, and the 4, 2 will be minus S. Okay, or in general what happens, so if you wanted to write in case of general matrix P comma Q, so PQ can be, P is any identity, any number, index. P can be 1, 2, 3, 4, whatever, N, or Q is also. So in that case, so what happens, so then we are having this dot, 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 somewhere else in between. So this matrix is being drawn for somewhere else. So then this can corresponds to any P, any row P, and this will be any row Q of our n cross n matrix, which is what the dimension of the matrix which are going to diagonalize. This will be P, and corresponding column also will be equal to P and Q. Fine. So this is the way we will construct our matrix, which is going to diagonalize our, this is Q. Which will diagonalize our matrix A. Okay, so, and now we will see how are we going to find out so somehow, let us try to find out. Somehow I construct this matrix P for which C is cos theta. Cos theta is given. So now what is the question is, what should be my C, what should be my S, C and S, such that this corresponding element corresponding to this S and minus S in my A matrix, I will convert it to 0. So what should be my rotation angle? What is my rotation angle such that when I take a P transpose A of P, so these two elements should become 0. Okay, how we are going to find out? That we will see it we will take up an example and we will see that will be more easier. And if you can take an equivalent from this rotation matrix and this matrix, if you see carefully, what this matrix P of Q is again a rotation matrix in a n cross n dimension. Okay, so what we are doing, we are defining the matrix A in n cross n dimension, and this is what for a 2 dimension when you rotate it. So when you take a n cross n dimension and you rotate the matrix by a small angle theta, so by rotating it, so we are eventually converting them into sum of the rotation angle. We have to find out certain diagonal elements, off diagonal elements vanishes, and keep rotating over all the n axis. Okay, all the n dimensions, do the rotations all the n dimensions, so that ultimately you find out your matrix will become a diagonal matrix. So this is what we do it in the Jacobi rotation. So to find out the algorithm, how we are going to find out this C and S, let us take up an example and perform this operation. What is the operation we will do? We are going to perform the operation P of transpose dot A matrix dot P. So let us do this product and try to find an algorithm. What is going to be our, and I call this as your A prime. So let us try to identify what are the elements of the A prime. Let us see how this rotation matrix we have constructed is going to modify the given matrix, the given symmetric matrix A, and we obtain obtain the resultant matrix to be A prime. How the elements of A is going to be modified. So to make it simple, so what we are going to do is we will try to do it for a very 5 by 5 matrix. Let us take the A matrix to be 5 by 5, and this is your A matrix. So and this is P of, in the place of P and this index, we are going to take it as, this is the second row and the fourth row, and similarly the same way you will get it. This is second column and this is the fourth column. So therefore this is a P23 matrix, and you are going to again multiply by P23 of transpose. So let us try to perform this multiplication of these two matrices, these three matrices. So first, when I perform multiplication of these two matrix, this is what we will get here, and what we get is, this is simple because what happened, so these all are 1, so therefore the first row will not get modified at all, only the second row, since the second row has a Cn minuses, and the fourth row, these two rows, after the multiplication of these two, only these two rows will get modified, and that's what we are seeing here. This matrix multiplication is simple, so you can do it now. And then I am going to multiply this matrix and this right hand side P. So what is going to happen now? So if you see here, here the column will come when you multiply it with the row and the column. So only the second column and the fourth column is going to modify, because they are the only thing contains Cn minus S and S and C. All the other columns, only the one diagonal element is there. So this multiplication is going to modify only the second column and the fourth column. So therefore this multiplication of this matrix by P transpose A and PQ is going to modify only those elements, only those rows and columns which was given by the index P and Q. In our case, we have taken the indexes 2 and 4. So now if you carefully observe, this matrix is still symmetric. Why? Because we know A matrix is symmetric, therefore A of Ij is equal to A of Ji. Therefore if you see here, this element and this element is also symmetric. You can keep checking for all the elements. This element is also symmetric, or you can find out for where else we have. So and this element and this is also symmetric. We can find out from here, this one and this one. So we can find all these elements are basically symmetric. For this and this is symmetric. So then what we see is this transformation of the matrix A into A prime using our rotation matrices, it's not going to spoil the symmetry. Therefore A prime will be still as symmetric matrix. So this is an interesting thing. So we performed even after multiplication, the matrix will remain symmetric, and now and not just that, only those elements are going to be modified which fall on the second row and the third row and the second column and the third column. Remaining all the other elements remains unaltered. So we don't have to really perform when we modify the matrix A1, we have to only modify those elements which have actually changed. Rest of the elements we can maintain the same as the matrix A. Now if you carefully look into it, how these elements which are modified, if you write, I can from the pattern you can see, you can write down the general algorithm as A prime, that's so this is the A prime matrix. I'm having A prime matrix. The element of A prime of Rp, where R is not equal to P or R is not equal to Q, so both are not there, so Rp at that cases, so what this element is going to be, CARP minus SARQ. So this is, and similarly A prime or Q will be equal to CARQ plus SARP. So this is for the case like this. It can be checked very nicely. So here our P and Q, so in our case P is equal to 2 and Q is equal to 4. So we have take R can be anything other than 2 and 4. So let us consider for the case of R equal to 1. So what you are going to have is A prime of 1, 2. Let us calculate the A prime of 1, 2. That's the first row and the second column. So if we see this, and this is what we are getting. A prime of 1, 2, CAR12 minus SA1, 4, because R is 1 and Q is 4. So let us take for other case of RQ. So if you want to write what will be for RQ, so that means let R equal to 1, and so that is A prime of RQ is R is 1 and Q is 4. So you have to find out A of 1, 4. So A of 1, 4 is first row and the fourth column, and that you can see this is A of Rp, S times A of Rp, and that's what we have done, plus C of A12. So this elements where R is not equal to P, this generally can be written as this way algorithm lab. So this is the algorithm which is going to modify those elements with R not equal to P or not equal to Q. And now let us go for the other cases for the diagonal elements. What happened then, if you see these diagonal elements falling on the intersections of 2 and 3 are going to be modified. So this one and this one. So how these diagonal elements are going to get modified is A prime of PP will be equal to C square APP plus S square AQQQ minus 2 SCAPQ. So we can find out this is the way, and this is for APP prime and then AQQ prime, because these both are not going to be of same form, there is a difference. So of course they will be different. So AQQ prime will be equal to S square APP plus C square AQQ plus 2 SCAPQ. So this is how, so we can check out for this APP prime. In our case P is equal to 2, so A22 prime. So A22 prime is this. So A22 prime is this. We can see C square A22 plus S square AQQ minus 2CS APQ, because A42 is equal to A24, that will be 2 times A42CS. So similarly you can do it for this one also. Okay, so and this way, so we have calculated, we have found out these elements and the off diagonal elements. Now we have diagonal elements also, changing the element. Now the important element is this, where A prime of PQ or A prime of QP.
a PQ or QP. So in that case, so what happens? So A prime of PQ and A prime of QP will be, from here itself we can write it out here. So I'll write A prime, A prime of PQ, we can see carefully A prime of PQ and A prime of QP are going to be same, because it is still a symmetric matrix. That will be equal to A prime of QP, and that will be C square minus S square into APQ plus SC times APP minus AQQ. So this completely defines, so this is the one, so this altogether is an algorithm which is going to give us our A prime matrix A prime. So this matrix, so this matrix is given by this algorithm. Only these elements will get modified, all the other elements will be remain as it is. See, something like this here, these elements are not going to get modified at all. So after the multiplication of P transpose A and P, only these elements is going to modify. So this defines the algorithm. After multiplication, this is what we will get. Now we have to choose the values of C and S, or alternatively rotation angles, such that this element of A prime and this element of A prime, which they both are same because of symmetric matrix, after this multiplication of after doing this transformation, so these two elements should become 0 in the Jacobi rotation technique. So we have to choose an angle such that these two elements become 0. So that will give us, we have to choose the angle from these two, from this equation.
So in Jacobi rotation, using this matrix PQ, we try to we get a prime matrix where only these elements will get modified. All the other elements will be intact. This won't modify other elements. Basically, as the corresponding the pth row and qth row, as well as the pth column and the qth column will be modified. And in this, what we want to achieve in this process is the off diagonal elements. That's what I'm going to mention. This element, I want to make sure after making that rotation by a certain angle theta, this element should vanish. This should become 0. So then if you see, if this want to become 0, I will write this will be, then you can do this simple jugglery and you can say if this wants to be 0, then you have C square minus S square divided by CS will be AQQ minus APP divided by APQ. So this, if these two are, if this is equal to 0, then we have this condition. Suppose if I multiply 2 in both sides, both the sides. So what we are going to get, cos square theta minus sin square theta. So this is going to be cos square theta minus sin square theta equal to cos 2 theta, and 2 cos theta sin theta is equal to sin 2 theta, and that will be equal to cot 2 theta. So this will be cot 2 theta. So this will be cot 2 theta, and so all we wanted to in this method Jacobi rotation is we wanted to find this matrix PQ where the PQ contains only C and S. All the elements are 1 and 0s, only C and S for 4 places we have. And to find CS, you need to know what is the theta. Then you have to find out the cos of theta and sin of theta. And this is an interesting equation which will tells you, given a matrix A, if these are the qth diagonal element and the pth diagonal element divided by 2 times of A of PQ, the corresponding off diagonal element, and if we take this ratio and twice of it, and then the cot inverse of this and half of that angle will be the rotation angle. And if you rotate your matrix, the given matrix, that particular component PQ by that theta, then these elements A PQ prime and AQ prime for the final product is going to be 0. Now, okay, for this we need to, what we have to write, so what I am saying is, so theta is equal to what? So your theta will be 1 by 2 cot inverse of AQQ minus APP divided by 2 times APQ. So this is the angle which is required to, this is a rotation angle. If you rotate by this angle theta, then the corresponding two diagonal element, or off diagonal elements will be 0. And you can repeat this rotation over different axes, and finally you can get a diagonal matrix. Well, to actually, if you see it carefully, we can still do some more jugglery, so that we don't have to really evaluate this trigonometric functions. Without evaluating trigonometric functions, you can find out this rotation matrix PQ. How we are going to do is, so let us try to write down. So let us write this one, C square, C square minus S square divided by CS. So which is equal to AQQ minus APP, or I know I am leaving this. So I am going to write this quantity as, say, something like 2 times alpha. So alpha is a known quantity, remember. Alpha is a known quantity because this is from the matrix A, you can calculate, and half of this one. I shouldn't do this, okay. So if we calculate this one, and that will be a 2 alpha, that's what we are writing. Half of that value is a 2 alpha. And now, okay, you can take cos square from outside, and then it will become what upon 1 minus tan square theta divided by tan theta will be equal to 2 alpha. Okay, so this is, I took cos square theta outside, so then becomes 1 minus tan square. So now if I rearrange it, what we are going to get is, this will give me t square plus 2 alpha t minus 1 equal to 0. This is a quadratic equation, and this will have a root t is equal to minus alpha plus minus root of alpha square plus 1. So this is the, and okay, fine. Okay, so this is the t we have. So remember, I am not using any trigonometric functions because alpha is known, so I get a t. So now if you know t, so you can see that t can have two values. So it can have either plus or minus. So what we need to see is, here is something important is, when we solve this A prime matrix to make this off diagonal element to 0, what we'll find out is the angle or the tan theta will get 2 roots of this tan theta. Whenever the tan theta will have 2 roots. So for both these roots, so for when either I take minus alpha plus on this value or minus value, for both these roots, this element which we want to off diagonal element will become 0. Now so we have 2 roots. Among these 2 roots, which one are we going to use? That is there with the magnitude of these 2 roots. Why it become magnitude of the 2 roots? So let us see it more closely. So for example, okay, let us go back into the same operation. So what is this operation we are having? We had this is second row, and this is the 4th row, and similarly the second row. So this operation, what we did is P of 2 4 transpose dot A of P of 2 4, and that we got it as a prime. Fine. So after performing this operation, so what will happen? These 2 elements will become 0. So now let us see. So I want to make I want to slowly, similarly I want to make all the off diagonal elements to be 0. So let us start. After this, if I want to make up say for example this element to be 0, I want to make this element to be 0. So that means this is corresponds to second column and the 5th row. So the when you make the rotation matrix, what will happen is
this second and the, so P will become, in our P comma PQ, P will become 2 and the Q will become 5. That corresponds to it. So what happens? So what we have to do is P of 2 5 transpose dot A prime dot P of 2 5. So we have to do this operation. So A prime is the earlier already we have zeroed this element, that matrix. So now when you do P of 2 5 and when you do this P of 2 5, this particular element, that is 5 comma 5 2 and 2 5, these two elements are going to become 0 when I perform this operation. But when I perform this operation, what we do, we are doing 2 of 5. So this operation is going to modify the second column as well as the fifth column. So now, then since the second column is going to, with all these elements going to modify, here in the previous operation we have already zeroed this element. Now the moment when I am trying to zero this element, this also will get modified. Okay. So that means it is not possible for me to zero all the elements. The moment I modified one element 0, the earlier element which I made to 0, that will get modified. So this we can't help it. So we have to survive with this. So the only way what we can do is how much it is going to get modified from 0, that we can reduce it. So then what I will see is from these two t values, the 2 root of t values, I will choose only that value which is not going to deviate the already zeroed element far away from 0. So then what you will see is that then in the later on we will see this each change of matrix elements after performing this operation can be expressed as a correction factor to the old matrix. That means this can be written as, that you will see it later on. So this all can be written as, so A of this is 2 comma 2, for example, A prime of 2 comma 2 will be equal to A of 2 comma 2 maybe plus or minus some correction factor. So and this correction factor will be a function of time, that we will see it in the towards the end of it. I will show you that. So this correction factor is going to be a function, will depend upon this tan theta. Therefore, choosing a smaller magnitude of tan theta is not going to modify your correction factor largely. So that's what, even though we have 2 roots, the one we will use only the one which has a smaller magnitude. So what happens? So eventually, even though we have made it all the elements 0, every element when you are making 0, it will modify the element which was zeroed in the previous transformation. So once you have completed all the off diagonal elements to 0, what you will find is it can never be, all elements cannot be 0, because the moment when you make one off diagonal element 0, there will be a small factor will keep on adding on the previous zeroed elements. So but what it gives you is after this completing one full operation for making this zeroing all the off diagonal elements, what happens is this matrix will get modified into a diagonally dominant matrix, whereas other elements will not be exactly 0 but close to slightly more than 0. Now if I perform this operation again and again repeatedly, if I use this Jacobi iteration again and again, so there is a time even though it keeps modifying, it changes to 0, that correction factor keep reducing smaller and smaller. At some point this matrix will closely resemble a diagonal matrix, and that's how in the Jacobi iteration, Jacobi rotation, we diagonalize a matrix A.
So among these t values, what we have to, among these two options of t, the one we have to choose is the one with the smaller magnitude. So then what happens? So then your t will be equal to minus alpha plus alpha square plus 1 if alpha is greater than 0, or minus alpha minus root of alpha square plus 1 if alpha is less than 0. So accordingly, we have to choose a one. The t has to be a smaller magnitude, so that our off diagonal elements, already the zeroed off diagonal elements will not become sizer, will not keep increasing its value. That we will see in the end also, how this is going to matter. Fine. So let us take this one. So now, knowing this t value, and what we have to, if I know this t value, it's easier to find out my c and s, because it's just a trigonometry. So your sine theta can be written as tan theta divided by root of 1 plus tan square theta. And similarly, cos theta can be written as 1 upon root of 1 plus tan square theta. It's easy to check. You can check by yourself. So with this, so once I identify t, then I can get my S and C, and that's all needed to construct my matrix P. So now, if you see in this process, we have not used any trigonometric function. What we did is, given a matrix A, and we want to make a particular off diagonal element to be 0, say that's at a PQ. So we will find out this quantity AQQ minus APP by APQ. So we will take the half of this quantity. The half of the quantity is alpha, and then we will find out t correspond and find out whether the alpha is greater than 0 or less than 0. So if it is greater than 0, then we will write t as this. If less than 0, then we will expect t as this. So once we get t, then straight away we can find out your sine and cos and use that in the matrix P, and that's what the matrix which is going to annihilate one of the off diagonal element corresponding to our P and Q. And now we have to repeat this process over all the off diagonal elements, and eventually the matrix should become diagonal. Now, as I told you, when you are performing the operations over a certain column, suppose for example one off diagonal element you made it 0, and when you go for the next element to the next element in the same column, so when you're making it 0, there will be a small correction factor will be added in our earlier zeroed element. So what happened after you making the diagonalize, after trying to diagonalize it one iteration over the Jacobi using Jacobi rotations, you are not actually going to get a diagonal matrix. What you have is diagonal elements will be dominant, even though you have zeroed all the elements, but the successive operations is going to have some smaller magnitude in the all off diagonal elements. Okay, so what happens is the diagonal elements will be dominant, but the other elements will not be 0, but they will be approaching 0. So what you have to do in a Jacobi rotation, you should not stop with that. Then repeat it again. Keep repeating again and again. Maybe something for iteratively, again you diagonalize it, the one. Okay, so when you keep diagonalizing again and again, eventually what happens, you will find out your matrix will be diagonalized, and those diagonal elements are your the eigenvalues. And then how are we going to get P? Okay, fine. So now before going to P, okay, P you can get it. So before going to P, there is something we can use. All right, yeah. So now, so one way is, see, remember when we are writing a program for Jacobi rotation, you are not supposed to do this multiplication. P transpose dot A dot P. If you perform this operation, multiplication, you found out S and C, then you construct your matrix P, and if you multiply it, and then you get your A prime. So this is not a very efficient algorithm to do, efficient way of writing the program, because you know the way we have constructed this matrix PQ, the rotation matrix is such that only the rows P and Q and the columns P and Q is going to be modified, which is given by this term. So what we have to do, we have to just replace this matrix A with the corresponding rows and corresponding pth and the qth row and the pth and qth column replaced by this algorithm. Once you do that, automatically what you are doing is you are getting A prime. You don't have to really perform this multiplication. And then again go for another one and keep doing it out. Just you have to keep modifying this A. And what you have to do next is okay, so that's the way you can write the program. And even there's one more thing. So you may probably that's another way of also doing. What happens? So if you find out the C and S, and then you try to find out these values, sometimes what happens, because of the precision of the computer, this is supposed to be 0. But since you find out C and S, because of the precision, this may not be 0. So another way of working out is, let me remove this one. Fine. Another way of working out is, so anyway, you given a matrix A, first what am I going to do? I am going to take a certain element. I will make this element APQ prime, which is equal to AQP prime. I will make this as 0. Simply I convert, give a matrix A, I will take one off-diagonal element to 0. And then I will see what will be the changes in my other elements what is given here. So now if you see, when I made this as 0, so from here we can find APP will be equal to APP will be equal to AQQ plus, minus C square minus S square divided by SC, C into APQ. So we got this from here. So what I did, we just changed this particular element to 0 and this give me this. So if I substitute this guy over here, let us substitute me over it here. Okay. So in the place of APP, I am going to do this. So you can see when I do, so what you are getting, so this will be S square, there will be one S square multiplied all over the sides. Okay. So then this, you will get an S square AQQ, so that this two will make it as C square AQQ and S square AQQ. We know C square plus S square equal to 1, cos square theta plus sin square theta equal to 1. So when you substitute that here, so let me write it down. What you are going to get is AQQ prime will be equal to C square AQQ plus S square AQQ minus S C square minus S square by C APQ and then plus 2SC APQ. So this is nothing but AQQ. So AQQ prime will be equal to AQQ plus, so what is this quantity? I made a mistake. Oh, correct. No, this APQ I can take commonly outside. So what we are going to have is, correct, 2SC minus S C square minus S square by C into APQ. Correct. Yes. You can do this trigonometry. What you will find, this will be nothing but your tan theta. This will be tan theta. So therefore, AQQ prime will be equal to AQQ plus TAPQ. Yes. Similarly, you can find for APP prime also. So APP prime will be, again you can write it as APP plus, here it will be minus T times APQ, and then we can find out, similarly you can find A prime or P, there also we can do out. Okay, we can express in terms of A or P. So what will you find is, this you can try by yourself. It's a simple basic trigonometry. I don't want to do that. S A or Q, sorry, this is A or Q plus, I am writing a term tau. I will tell you what tau is, A or P, where tau is tan theta by 2, and you can express that this comes from 1 plus c. You can check it, that's nothing but tan theta by 2. Okay, so we can do this same jugglery and we can write it in this form, and then A prime or Q will be equal to A or Q, then it will be plus S times A or P plus minus, it will be minus tau A or Q. Fine. So this is and so what we have done, we have redefined the algorithm, which is how our matrix is going, how the rotational matrix is going to modify into a different form. So this algorithm, which is going to find out what are the elements which is going to change because of this operation of this PQ, we have redefined the algorithm in this form. And the advantage of expressing in this form instead of this is, you can see basically you can see these all are an incremental factors, small incremental factors, whatever you can, small or whatever you can call. So whenever given a matrix A, pick up those elements, only those elements for which you want to make it to 0, make this APQ and AQP as 0, and then AQQ prime, write like this, AQQ plus some correction factor, APP prime will be APP minus this some correction factor. You can see this is all the correction factors. Now if you see, all these correction factors contains the value T. Okay, so the correction factor has to be smaller, because what happens, once you make zeroed a certain element, when you are making zeroing the next element, there is a small factor is going to be added because of this. Every element will get added by a small factor. The moment if your T is very small, then that adding is going to be significant. Okay, that's what when we took this quadratic equation of T, when we are solving, always took the smaller magnitude of T, not the larger magnitude T. So that this correction, even the zeroed element becoming, adding some more element values to that 0 is not going to be larger. So this correction factors has to be always a smaller value. So this is the way you can keep doing for all the off diagonal elements, make it to 0. Though in one operation it won't become 0, you have to repeat this operation again and again, and thus we can get the finally you can diagonalize the matrix A, and the diagonal elements will give you the eigenvalues of the matrix A. So the beauty of this algorithm is you really don't have to use any of these trigonometric functions, sine or cos or anything. Given a matrix A, find out alpha, and once you find out alpha, then you can find out T. Once you find out T, you know what is the correction factor should be added in each element. And just do it repeatedly for all the off diagonal elements, and that's it. And then you got the matrix A prime. So this is the beauty of this algorithm. And only thing is, it's a very lousy algorithm because you need to do many operations, keep on doing operations. So that's one of the points. So there are better algorithms which I leave it you people to read by yourself, the householder's method and all those things to yourself. Okay, so this is the way we got our eigenvalue. To get the eigenvector, what we are going to do is, so what I wrote for eigenvector, the collection of right eigenvectors will be equal to all the matrices which we are which we use to diagonalize it. We have to keep multiplying all the take a product of all these matrices, and that's what is going to give you your right eigenvectors, collection of the right eigenvectors. So how we to do it is start with the matrix V, make it as an identity matrix. When you perform the first operation, what you do, then you write your V prime, which is I times, okay, sorry, I would call it as, so, yeah. Okay, fine. So, I times V1. And then make your V is equal to V prime. I'll call it as P. And keep doing this cycle repeatedly. So what happened? You started with V equal to I, and then when you're doing the first rotation, multiply that P with that I, then redefine your V prime as V, then go back. Keep doing this cycle. So when you finally end up, when you extract the matrix V out of it, that's nothing going to be a collection of your eigenvectors which you wanted corresponding to those eigenvalues. So this is an though it is not a very efficient method, but it's what you call it is a sure shot method. If your matrix is symmetric and real symmetric, and if it is non-degenerate eigenvectors, then this method is surely going to give you the eigenvalues and the eigenvectors. That's why this method is being often preferred by many in finding those eigenvalue problems.